Good evening, everyone. Can you hear me clearly? I am Sandeep Giri. I'll be the instructor for this session. I'll be going ahead with the first introductory session. In this session, so basically, let me introduce before myself uh, about No Big Data. No Big Data was basically started because I realized that there is not many people in the industry who know anything about big data and they are teaching big data. So because I happened to attend, my friends were attending some classes somewhere, and when I looked at the content, I realized that none of them is basically, I mean, they're not doing justice, right? So that's why I said, Ki, why don't I train you guys? Why are you taking classes elsewhere? And that's where I started this No Big Data. And they found it really interesting. They found it really, really good. They blogged about it. And that's where I started No Big Data. And that's when I realized that I'm pretty good at training. So I built a team and then we started. So the main focus is on asking questions, and feel free to ask as many questions as you wish. The other part is that we focus on the real experience. Therefore, we have set up a cloud labs the way it is generally set up in any big data company. Okay. So generally, there is the most of the softwares the way they are installed in any big data companies. We have set it up for you so that you have a clear picture on what kind of things you will be working on. Okay, because everybody was working on virtual machines, this and that. I realized that's not the way to go forward. Therefore, we set up the cloud lab. We call it cloud labs. It's a cluster of computers, and rest is just. Rest. We focus a lot on helping you with the big data problems. Okay. About myself, I started my career in 2002, finishing my BTech chemical from IIT Roorkee, and afterwards I was like one of the chief programmers of the college, and then for DE Shaw, I was building a large big data systems before the term was coined. So for a quick idea, we had a 10,000 computers in a grid. Okay, before big data we used to call it grid. Now it's called big data mostly. Not both definitions are not one to one, but we'll talk about it later. So there I was handling few terabytes of data when people were not able to handle gigabytes of data at DSHA. Then after DSHA, I started a company called TBITS Global, and that built an enterprise grade document management system, and that's still running and going good. Okay, so that is I have taken an exit from that company. I worked with InMobi where I built recommenders and high throughput systems. The recommender was churning around 200 terabyte of Apache logs and basically giving one of the best recommendations. Now, and high throughput systems such as real-time analytics, I was working on at InMobi after recommender. Now, I worked with Amazon on similar high throughput system using Amazon's similar to the No Big Data solutions, as well as built something like Apache Storm for Amazon. All right. Now, then in 2014, this year, I've started No Big Data. So that was about me. Today, we are going to discuss understanding the big data and then going detailed into Hadoop architecture. All right. So in case you are just looking for introduction, this class will be more than sufficient for you. All right. In case you face any questions, any doubts, feel free to drop us an email. We answer your questions as much as possible. And we will be soon launching our online forum where you can ask questions and we will be answering those questions publicly rather than over a ticketing system. Right now we have a ticketing system to answer. Okay. Now, in today's class, these are the various topics, right? So let's jump in. All right, we have 28 attendees in this session. This is the first session. All right. So, what do you mean by big data? Just put on your understanding so far, okay? Quickly. And I missed one introduction by Rashmi. Rashmi is based out of Bangalore and a freelancer developer. Okay, I did not miss. All right. So what do you understand by big data? What is your opinion as of today? It's about, Koya is saying that it's about size of data and terabytes of data. Okay. Hi Madhav, everybody is muted. All you need to do is click on the questions box and ask questions. All right. Subhash is saying that it's a large volume of data flowing in high velocity in different forms. Okay, okay. Large volumes of unstructured data. Okay, okay. So Vishal has already attended my first session on YouTube. Oh, great. Oh, great. So it will be the same repeat cast of the same thing what you had attended. So you can, if you wish, you can skip. If you have questions, you can ask. Hi, Chandra. Okay. So Ambu is saying amount of data which is very huge and which is very difficult to handle. Srinidhi is saying huge amount of unstructured data, large, and then okay, okay. Nitish is saying big data is the science of extracting useful information from the large unstructured data. All right, all right, okay. So it's about how organizing and retrieving huge data efficiently. All right, all right, all right. Excellent, excellent answers, excellent answers. Okay. Chandra's point is to process large data from different types of data in faster way. Excellent. Okay. 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 Ramesh's question answer is that large chunk of data for analytics purposes. It's about dealing huge data and getting useful. All right. Quick question. Yes, Sanjay. Sanjay, it will be the same session which you had attended earlier, so you can skip it. But if you have questions, you can ask. All right. Awesome. So we have got great set of answers, and all of you have actually, you know, defined it properly. Now I'll just concretize the definition a bit, and maybe it might be a little bit of our kind of definition, but we'll stick to the definition what we are giving. All right. So what is big data? Big data is not a science we refer, though lots of people refer big data as itself a science, as Nitish put it. But big data is simply huge data. Okay. So let's not confuse the terminology. Whenever we have to say big data science, we'll say data science or big data science or analytics or some sort of insights, right? But big data will refer to just huge data. Okay. And what is that size of big data at the point we start saying big data? That's something to be discussed. So that size should be such that size, speed, or whatever the kind of data the we are talking about is something which cannot be processed with usual tools. And when I say usual tools means our usual RDBMS kind of tools. And relational database management system is something like de facto for managing the data everywhere. And most of the RDBMS are pretty efficient at handling the data, probably better than any other systems like file system or any other systems to handle the data. Now, so the data of very big size which cannot be processed with usual tools as in RDBMSs, and for to process such kind of data, you generally need distributed architecture. And what does it mean by distributed architecture? Distributed architecture means multiple computers to solve your problem concurrently, and that is distributed architecture. Okay, a cluster, a multiple computers, or a cloud of multiple computers. Okay, So a cloud is generally cloud. When I say cloud, cloud is generally mean to say a computer or a group of computer at somebody else's place. That is cloud. All right. And the fourth is it can be structured or it can be unstructured. Okay. So structured, unstructured does not define big data. The matter which defines the big data as, you know, when we say a data as big data, the moment we hit a roadblock saying we cannot process this kind of data with our RDMS, we require new generation tools which can utilize multiple computers at the same time to solve a problem. And trust me, already there were people had been building their own tools even before the term was coined to handle such a large data. Okay, so they were in a tangential way. They were all build, like at D show I was handling uh, uh, terabytes of data in 2002, right? I mean, our data was so huge that we could not transfer it through the internet. Every week we used to get a tape drive from US to India via ship. Okay, so now you can imagine the size of data. The size of data where the speed of electrons is slower than the ship. Just the sheer size of the data. Okay, so therefore there were tools already, but those were not generally available tools. Those were like a very secret systems. Okay, we were not about supposed to talk till 2004 about our cluster. So Dave's point is that would you consider IoT sensor data to be big data? Yes, mostly yes, because IoT sensor data is so high. If you have like 10 sensors and they are giving you data every second, okay, in some circumstances where I am working with few people, they have sensors which emit the data every say tenth of millisecond. And in managing that kind of data, you require high throughput data, high throughput systems, as well as systems which can manage huge data on the back end. All right. So mostly IoT is Internet of Things. Internet of Things, as in all the things the people have started connecting, starting with television, starting with your everything they have started connecting, all of them being emitting their information to a central place, and then being controlled easily via internet. All right. So Dave, was I able to answer your question? So mostly yes, IoT sensor data ends up being big data after a few, maybe 2 months of data. Right. So, okay, Shiva's point was regarding our mechanism. We used to bring data from US and New York to India. And he's saying that what if one ship sinks? We have a backup of data in US anyway, right? We were just getting the data from there to India for the analytics reasons. IoT means Internet of Things. Okay, great, great, great. So, moving on. So, this is the classic definition which is given by IBM before before when you're talking to somebody and they ask you big data, please give this answer because that's what most positive people are expecting the answer. But when you are really implementing things, go with this definition that when you hit a roadblock with your existing solution and you require distributed architecture, I'll help you figure that out. How do you reach to a point that you know how do you reach to the point that you need a distributed architecture? Okay, so you stick to this when it comes to practical, but when people ask you the definition, this is something most of the people are expecting. So this is the IBM's way of defining big data. Earlier there were 3 V's, now 4 V's, and probably this year they are adding one more V to the definition called value. And I don't know, next year few more V's. And right. So what they are saying, that the way you define big data, these are actually characteristics of any data, whether volume, velocity, variety, or veracity. These are general characteristics of the data. Okay. And because of any of these characteristics, any of these 4 characteristics, you might end up using any of those big data solutions. Because of any of these 4 characteristics, your data might end up becoming big data. All right. Now let's define what we mean by that. So volume, if your data is too huge to be handled by one computer, in terms of even the data, when your data is sitting silent, then also it's a big data at rest. All right. And this data, I mean, I'll tell you why do you need a distributed architecture for the big volume. Okay, in just a few minutes. So these are the few examples, like what Facebook stores per day and what they have been storing for years. And then velocity. Velocity is something interesting which most of the people try to escape. Okay, so let's take a case of a stat counter. Stat counter basically counts how many people visited your page. Although there might be a million people visiting a page in a day, those million requests will actually change few numbers on the server if they are not logging, right? So even though the volume is smaller, but the velocity is too high that you need multiple computers to handle this kind of load. And therefore, to handle such kind of velocity, such kind of need from the user side, we might end up becoming we will have to use multiple computers parallelly to solve various kinds of uh, you know handling of the requests, right? Therefore, velocity itself can be can make a data big, can make your problem a big data problem, and you might require a big data solution, right? Now third point is variety. Variety, let's take a case of your videos. So all I'm trying to prove in this discussion of these 4 V's, that any of these 4 criterias can make your data big. It's not and that your data has to have a high volume as well as high velocity as well as high variety or high veracity. It means e either of these 4 parameters can make your data huge, and that you need to look out for. I mean, any of these 4 parameters make your data big. You will start calling it big data because of any of these things, right? Now, variety. Now, let's take a case of videos. Even though your videos are 200 GB in size, okay, and they are staying at rest, so they don't have a high volume, and they don't have a high velocity, right? But they have got variety, multiple kind of codecs, multiple kinds of frames. And because of the nature of the video, there's a and say you have to just analyze a lot of things in a video, right? You have to learn from frames, you have to do a compression parallelly, and all sorts of things. Okay, and say half of your data is in video and half of your data is in subtitles and half of your data is in say translations, right? In those cases, just because of the variety of the kind of data, you will have to use distributed computing to solve your problem. Okay, so I was discussing something with the national labs, if you are aware of national labs. Okay, so part of NASA basically. So what they're trying to do is they are taking a satellite capture from the top, and anybody can ask for the detailed information from around the globe about a small rectangle. Okay, for that, the solutions they had hit a roadblock of the response. Now they are moving it to a big data solution, and I'm working with them now. Just because of sheer, first is volume is say few terabytes data every month, and that's not too big a data, to be very honest, that can be handled with the that was being handled already. But because it's maps and there are multiple layers of imagery they do, because of sheer geospatiality and time lag, I mean temporal data, every second they have multiple kind of frames. Because of the variety and the complexity of the data they're storing, it is turning out to be that the existing solutions they built are not efficient enough to handle that sort of need, and therefore they are moving to big data now. Okay, so that is the role of variety which is playing. Similarly, if you have say a 100 GB data of Google Maps, or some any maps, right? And you have to find location, you have to find a route from one position to another position using and by various kinds of channels. It's a big data problem. It cannot be solved in a reasonable time with a single computer. You need to have really brilliant solutions in the back end who can run parallelly to find your solution, right? So variety makes a classic case of big data. Okay, and and that is why lots of people think that variety is the only candidate. No. All right, the other point, which is fourth one, veracity, that has been probably added just like that, but I'll justify it, and so that you can also explain to people. Okay. Yeah, I'm being funny. Yes, this session is being recorded and will be available to all later on. Great. Those who have attended this session already, they can skip this session easily. If you have questions, drop me a mail. All right. Now, the fourth parameter is veracity. Veracity is just a data in doubt. All right. So there are a lot of data you encounter in an organization which you feel that we already have the main data, but you are not so sure that you should keep it or do not keep it. And just by virtue of the confusion, you end up storing that data, processing that data to figure out whether to keep it or remove it. What could it be? What could be the examples of such data? Say interim data of any statistics. Okay. So you had, say, a data called population of Indian states, population of US states. Now, you know that there would be a data we have which has a far more detailed version of this information, such as population zip code wise. Okay, so till the point you figure out that we have such a data, we keep this data. The other reason you might keep it by doing a quick computation, that whether it takes a long time to reach to this data from the previous one, or is it quick. So because of all such kind of doubts, you end up keeping a lot of data, and that is what is called veracity. Okay. All right, so all right, so just to check whether you are sleeping or not, my question to you is, how many bytes are there in a petabyte? Just quickly. 10 to the power 12? No. 2 to the power 64? Okay, can somebody tell whether it's correct or not? Okay. Dave is saying that 1 followed by 15 zeros. Good, good, good. Awesome. Okay. Yeah. So let me answer Madhav's question. Madhav is asking, is it isn't possible to update existing data from a big data tool like Hadoop so that we do modification to existing data. So the way most of these big data solutions have been built is generally, I mean, they can definitely update the data, to be honest. Say, for example, HBase component, you can update the existing data. All right. It is just that normal file system is append only. The HDFS is append only. And therefore, it doesn't edit the data. But the database, which HBase kind of database, help you edit the data. Anjani's question is that those days to handle large amount of data did have millions of servers. Now also they do the same. What exactly does distribution means here, and where does big data fits now as it was those days? All right, that's a very valid point. Very well. I will answer this question in a minute. Okay, I'll answer this question with the proper, because there's one slide and I love to answer that. Okay, and even if I'm not able to answer, just remind me once that I could not answer. All right. Excellent. So yes, almost everybody is correct. So it is 10 to the power 15. Even if you don't put this one, this number in front of it, it's still okay. Okay. Now, these are the, this is the way you can remember it. Kilo, mega, giga, peta, tera, exa, and that's not a big science. Okay. Just because we'll be talking too frequently about petabyte, exabytes, and all, so you should, have a look at it. So kilo, mega, giga, tera, peta, and every time you multiply 1024, and 1024 is basically 2 to the power 10, and this one and this one is basically you keep on multiplying 1024 every time. So kilo, mega, giga, tera, peta, and so on. All right. So here tera is 1024 to the power 4, and peta is 1024 to the power 5, which means 15 zeros. Okay. Okay. Praveen, in this one, we will not be able to do that. So Praveen's point is that can we see what others are asking? I too wanted to do that. It is just that from the second session onwards, everybody will be able to see. Okay. This is a general session, the introductory session for all. From second session onwards, everybody will be able to see everybody's questions. Okay. I always wanted to have that kind of model, but webinar, GoToWebinar does not provide. GoToMeeting does provide us that. So from the second session onwards, we'll be using GoToMeeting. All right. Now, so this is what my petabyte looks like. Now, question to you is 1 petabyte data big data in your understanding? So we talked about what is big data. Big data is something you can't handle with the usual tools, and you might have to use multiple computers. Okay, that means most of the solutions we see as of today are single computer, so single the software that runs on a single computer efficiently. Now, is 1 petabyte data big data or small data, usual data? Meaning, can you process 1 petabyte data using any of your usual tools in a single computer? Even if that computer is, say, a supercomputer, can you handle 1 petabyte data? Even let's say storage. Can you do a storage of 1 petabyte data efficiently on a single computer? If you can't handle it using single computer and using usual tools, then it is big data. All right. So Shivaji is the how to register for others. I will guide you. Don't worry about that. Okay. So Dave is saying that yes, he'll consider 1 petabyte data to be big data. All right. Great. All right. So yes, 1 petabyte is a big data because handling 1 petabyte data, even if you have a supercomputer in your office, is really impossible. Okay, and therefore 1 petabyte data is generally considered big data because the basic thing you can do with the data is store it, right? That's the first thing you can do, and even storing 1 petabyte data requires really brilliant solutions. Storage can be done. I mean, that is Shivaji's point. But so far, Shivaji, what I've seen is that when you say storage, you also need to talk about backup, failover, and making it available for users. Okay? So all of that, if you think about, most of the existing systems fail pathetically. So Nitesh's question is, so 1 TB is not generally a big data. Okay? It depends on what kind of processing you want on 1 TB data. Storing 1 TB data is not a big deal, but processing 1 TB data might make it a big data because you cannot maybe you have a requirement, say 1 TB movies. If you're just keeping in your hard disk and all you're doing is watching it, you don't require a big data solution for that, right? It all depends on what are you planning to do with those 1 terabyte data. Okay. So Nitish, I was I able to answer your question? Now, excellent, excellent. Now moving on. So this is a general story of how data has increased since 1968 to 2007. The digital storage has expanded dramatically, okay, after 2002. And why did that happen? While analog storage actually shrank. Okay, the upper colored section is analog and lower colored one is digital storage. And why did that happen? The simple answer is devices and connectivities. Simple answer is devices and connectivities. Devices became cheaper, smaller, and faster. Okay, every company had been working really hard in the hardware domain to make device. They have three basic demands: make it cheaper, make it faster, and make it smaller. And that they have been doing marvelously. And that happened specifically in terms of smartphones. Every chip got smaller, faster, and cheaper. So that was the first reason why it happened. The second reason, which is more important to understand, is the connectivity. The internet connectivity or connectivity between things became so abundant after 2002. It kept on increasing, and that is the reason. And when we say connectivity, connectivity can be between things, connectivity can be between people. First came the hardware, then came these solutions like Facebook, YouTube, and all the sort of social network which make people record and share their content with everybody, and that have changed the whole paradigm of the rate at which the data has been increasing, and that has led to exponential data. And when we say exponential, what does it mean? It means the rate of change of data is proportional to the data we have, and even more than that, right? And that makes it exponential. And the exponential growth is mainly because of connectivity. Because when you connect, and say the way I'm speaking right now, the total data transmission is happening will happen by the end of this session is around 26 GB. Okay, if I'm assuming that my my upload is 1 GB in 3 hours, okay, my recording, the data which I'm pushing from this side, audio and video, will be actually close to 2 GB. All right, so by the end of this session will be I would have transferred close to 52 GB data. All right. So that is the magic of the networks. And that is what increases the data need. All right. So connectivity and smartphones is something that made it possible to do this. Now I'm answering one question which Meenal asked a little while ago, that though these systems were earlier also, what is it that had changed? So in 2002, when I joined Deisha, the solution we were using was for the banking one, and that kind of data was only available at that time to only few companies who has their established channels to gather the data. Okay, and those who have realized that this data is important, right? There was no Twitter, nothing. So but now in today's time, even a smaller company like mine has a demand of a huge big data solution. Why? Because producing and storing the data has become very easy. Second, I know that it's possible to handle such kind of data, right? So the data abundance and availability is quite high now as compared to the earlier days. All right. So that is the reason why it is so much in need right now. Even a smaller company like mine accumulates a lot of data from the website itself, from the Apache log itself, and I need to churn that kind of data. And as it will, earlier that was not the case. Earlier, that was not the case. Even a company like mine, I'll come back to these later. You will, by the end of the session, you will understand. That's a very, very profound question you have asked. All right. So by the end of this session, you will understand why it has become this way. Now, so now let's talk about handling the data. What do we mean by handling the data, and what all is required? Okay, so handling can mean storing, handling can mean processing. Okay, and these are the four pillars of computing on which probably every computer scientist would be knowing about it, and everybody, all of you would be knowing about it, but we'll just go through it once more. So CPU, everybody knows about it. It is just the logic gate which reads your instructions and then basically does the flip flops to execute your conditions. So CPU is measured in gigahertz, and CPU has been itself increasing at fast pace, right? Second one is the RAM. At what rate? RAM is a random access memory. Okay, RAM's property is that the reading from RAM is very fast, and therefore CPU reads quickly from RAM and stores back the results. All right, and the size of RAM is really matters, and speed also is one of the big criteria. You'll understand why. And when I am saying RAM also I'm referring to L2 cache, L1 cache, and all those things, in which CPU keeps the data into that random memory, and and reads and writes to it. All right. Now, third one is disk size and speed. We never considered disk to be a part of the computing. We always thought that higher the RAM, better the computing, higher the CPU, better the computing. But disk does matter. If your disk is smaller, when the data is smaller, we never thought that the data would not fit into the disk. But as it turns out, that the whole bottleneck in the game is generally the disk size and speed. Okay, even a smaller machine, a computer like our website, even though our website runs on a very low end CPU and low end RAM, but it has got very fast speed hard drive which has got SSD rather than a traditional one. And it turns out that our website never needed that much of a CPU or RAM. Okay, all it needed was a very fast paced disk reads and writes. So disk reads and write does matter a lot when we talk about big data. Now, or any data processing for that matter. Fourth one, network is very important. You will come to this point very quickly. So Let's take a case of that you got very huge data. Your data started increasing. You were storing it in hard disk, and after some time, you had to move the data to multiple hard disks connected to multiple computers, which means now the data has moved to the network. For one computer, other computer is in a network. And if one computer has to read the other part of data, it has to go through the network. And in case your network is poor, your processing is going to get hit very badly. All right. Now, as hard disk was slower, so people started moving the data to RAM. That's what we call cache. And if your RAM is insufficient, your overall handling is hit. And therefore, all these four components matter a lot. And going by the same proposition, if you add two computers in a network, you are actually adding all these four resources, which means that this is 16 times of resources you are adding as opposed to the general perception that you have added only twice. Because these four bottlenecks multiply in their behavior when do you do the computing. Okay, so the best case scenario for you is when you are using two computers and you have really built a great solution, then your performance will be more than twice when using multiple computers. Okay, so that's a general perception that okay, we just increased our hardware to two computers, spending twice the amount of money. Why couldn't we just vertically scale? Vertical scaling means we increase the CPU, we took out the old CPU and we put a new CPU in the same computer. Similarly, we added more sticks of RAM into the same computer. That is called vertically scaling up. Okay, it's like saying that the bull which were pulling our cart was weak, so we bought a bigger bull, right? That is vertical scaling. And horizontal scaling is adding two bulls to the same cart or adding hundreds of bulls to pull the same cart. All right. So that is horizontally scaling. So when you horizontally scale at the same price, you get far more. I mean, on the double price, you get far more value as compared to if you vertically scale, you might pay 10 times more to buy a blade server, and yet your processing is hardly doubled. All right. So that is the power. That's the power of distributed computing. And these four components get doubled, all four of them, when you add one more computers. And when you add one more, then they get tripled. And that's where the magic lies. All right. Now, so at least whenever also on the same premise, we can say that at least one of these components will become the bottleneck. All right. Now, these are the example use cases of big data solutions. I will go through the examples which I personally have worked on. So any questions till this point? If you have any questions, just feel free to ask. I might take a minute or 2 minutes to answer your questions because I would be finishing the topic. All right. So the first example which I had been working was the recommendation engine. Okay, recommendation engine, why does it require big data? Okay, the good, I mean, first let me explain what is a recommendation engine. When you visit Amazon, when you visit Amazon, you see the recommendations, right? Saying you may also like this, right? That is recommendation. And in our personal lives, we had been doing recommendation for each other for ages since the humankind. Me and say, let me just pick up a name. So let's say me and Nitish have 5 movies in common, and we both have watched 6 movies each. If we have 5 movies in common, the extra movie we can recommend to each other. We can say that me and Nitish both like Matrix, we and Nitish both like Shawshank Redemption, and hence such similar 5 movies, and therefore we are quite similar to each other, right? Now the question is, such kind of thing was always there. What is so big deal about big data, about recommendation? Thing is, recommendations are better when the data is more. When we have 10, 15 people sharing their behavior very much, we have a bigger cluster who are similar in nature, we can confidently, with more confidence, we can say that these 10 people are similar in nature to a 80% level, and therefore rest 20% we can recommend to each other. So number of recommendations increased because the data got increased and the precision got increased, and therefore the bigger the data, the better the recommendation. All right, the bigger the data, the better the recommendation. If you have smaller data, there are high chances that the recommendation which we are giving are very skewed. Okay, it just so happened that me and Nitish liked 5 movies, and therefore we just said ki, okay, we are very similar. There are high chances that if we had 50 movies, we had a data of 50 movies of Nitish and mine, there are high chances that we only like 5 movies out of 50, right? So therefore the bigger the data, the better the recommendation, and closer is the success rate of recommendation. Therefore, and this recommendation is one use case. We call recommendation as a collaborative filtering also. There are multiple algorithms we'll discuss in classes how to do the recommendation. We will walk through a case where we will take one algorithm of recommendation engine and take it to the end, starting with the raw data. Okay. Now, all right, now we have so I described, and these all use cases are in production. People are using these already. These are not some theoretical concepts. Then is ad targeting is not a common use case for all, but for few companies I have worked with and seen that ad targeting requires a lot of data processing as opposed to the common psyche. Okay, like I was talking to a trading company, I mean not trading, electrical company. They are setting up smart grids across, and what they are doing is doing planning to open a bidding platform, which is exactly similar to what we did ad targeting. Now, what is ad targeting? So now imagine that there are you are I mean, let's look at from the companies who do the advertising, such as Google, InMobi, and others. What they do is they take a lot of ads from various companies, and they have given toolkits to all the game developers to embed their real estate into games, so that every game developer gets some money by showing the ads. Now, when the users are playing that particular game or using that particular app, ad is displayed, and there are million users which are showing that ad. Okay, and you have got few servers which are serving the data. You have got 10,000 ads in inventory which are candidate to be displayed. Now you have to show the most relevant ad to the user so that he clicks on that ad and gets some useful output out of clicking that ad. You might get a relevant ad and what you have been looking for, right? And the things which you like. So the more relevant the ad, the better your system gets. The more clicks you get, and the whole purpose of advertising gets solved. So the relevance is the most important key in the game. And when you do relevance, you have 10,000, say 10,000 ad to be served, and maybe 10,000 requests in that particular minute. Now you have to figure out on various conditions like bidding behavior and all sorts of data, and that's where the complexity comes in. And you cannot handle any of such load using single node. You need to have hundreds of computers running for the same thing, and therefore people have to move to big data for these kind of solutions. Similarly, search quality might look like it's only a Google's problem, but no. Even a company like mine, which was T-Bits Global, it was an enterprise company, and we had hardly 10,000 users per instance, and still, and the data was hardly 50 GB for us to handle. Not 50 GB, it was around 200 GB, 80 GB a year. Okay, so we were accumulating data around 80 GB a year per customer. Now, even though the data is smaller, 80 GB, but search quality would require you to do a lot of churning of the data, not your data, but global data. Imagine building a beautiful dictionary or a thesaurus so that when a user makes a mistake, you give him a recommendation. Did you mean blue and space dart when the user types BLOO and DART? And that is the ability to give the recommendation, right? And based on lot of parameters, building a dictionary from Wikipedia, building a dictionary from a common corp of generating, say you have to build a tuple recommendation. When user types a happy, you have to give him birthday as a recommendation, right? To build this kind of information, you might need to crawl the data from across the globe and then churn it. So even though your own data is smaller, but to do such quality really well, you might have to process other kinds of data and dictionaries to fit it into your needs. If you really want to build a search quality, and to build a search quality is the holy grail of everybody. Okay, Amazon has a great search team they keep on improving every day, and same is with lots of people. Okay. Yes. So FMIC is, I mean, Clayton's question is that when we download apps and the message people who downloaded app A also downloaded B, yes, that's also a recommendation engine and also known as collaborative filtering. Okay, it's called people to people recommendation or this is called product to product recommendation. Okay, and some people refer to as cross selling also. All right. Now, on the same lines is sentiment analysis. Even though you are a small company building your brand, you might have to do a sentiment analysis of your brand to evaluate how are your marketing campaigns performing. So what does it mean by sentiment analysis? Understanding understanding whether people are talking good or bad about you on social platforms. So a very rudimentary way of doing it is that you crawl the data, find out the positive keywords and negative keywords used with your brand name, and then you do a summation of positive and negative, and then figure out whether we are overall positive or negative. And this figuring out this positive and negative again requires you to build a dictionary of positive words and negative words. Okay, and so all you need to do is crawl the data from all across the world, and the cheapest way is to crawl the data at Twitter. They give you 2% a sample, a small percent of the total sample of the data, and you can understand what people are talking about you, whether positive or negative, by evaluating all the tweets. Amazon does it to a very large scale. Forums and tweets and everybody, they crawl it continuously to build the to figure out the sentiment for a particular product they are selling. That gives them a clarity whether to promote that product or to take it offline. All right, so that is called sentiment analysis in general. Okay, sentiment analysis is getting sophisticated every day. Okay, because sentiment analysis also might require natural language processing, finding the context of every keyword, because people might phrase their sentences in multiple manner. Even if you do not do natural language processing and you are just doing a simple summation of all the positive and negative, still by the virtue of big data, you will get the right results, fairly right results, because the anomalies, which are rare statements which sound negative but are positive, or but sound positive are negative, are lesser as compared to the straight sentences or straight phrases. And therefore if the bigger the data you have, the percentage of anomalies keeps on reducing, and the other part keeps on increasing. right? And therefore, sentiment analysis, if it is done on big data, and even if your algorithms are not very sophisticated, it still results really well. Okay, it still gives really good results. Now, abuse and click fraud detection, that is something very important. Like anti-money laundering I had been doing at the show earlier, it required churning a lot of data from various government sources and comparing all of the government sources against the data we had, our transaction data, right? We have to make sure that this person is not listed by any by government or any agencies with list terrorist data. And the kind of churning we had to do was matching phonetically as well as figuring out whether user did a typing mistake. So SA and DEEP matches with SU and DEEP with 98% of accuracy. Okay, so we had to do all sorts of magic while doing a fraud detection, and this is a very important and emerging domain, and is something very important to very small company also. So similar is the case of telecommunications. So all I'm trying to say is that people are already using these solutions to all of this, and even if your algorithm is not greatly sophisticated, even if your algorithm is just average, summing up and computing average on a big data, still you will get a result which are marvelous. Okay, so that is the summary of all of this. In telecommunication, people had been using this, and this data, which these all case studies are from the Hadoop use cases, from the Hadoop's website, Hot&Works and Cloudera, and what customer testimonies are there. So based on that, I have gathered this data. Similar is this case, like government uses it, healthcare and life sciences uses it. Today, it seems that there is nobody from life sciences, but generally there are at least few people, few researchers from life sciences in my session. Okay, and so they are using it, they are using to a large extent, and that's why people come and attend these sessions for in life sciences. Okay, so and other than the main people in this industry, these are the general general statistics of 2010. And the bigger the word, the bigger use case, the more number of Hadoop instances are there. So Yahoo has got maximum number of instances, while InMobi has got okayish, and Facebook has also got quite high, eBay has got high, and so on. All right, now these are the common myths. You can read about it later, it's not something worth it. Now I'm skipping those two three slides, that doesn't matter right now. Now, all right, so we are going to discuss now what is Hadoop, and then we'll go into two components called HDFS and MapReduce to understand what is it. All right. Now, in this is a general the way we teach history, that it was created by dog cutting from Yahoo. And so basically, dog cutting was working on his personal project called Nudge, and he needed some really great storage. And in the right time, Google came up with a paper of Google file system, and he implemented that and started calling it Hadoop file system. At the similar time, parallel time, Google published MapReduce also, and he implemented MapReduce also on top of Hadoop file system, and that became Hadoop. All right. So that the whole combination of MapReduce and file system became Hadoop, and that's how it started. And it's absolutely open source. If you are using Hadoop, you do not have to buy or pay anyone unless you require support. Okay, you are free to make changes. You have no obligation of committing it back as per the Apache policy, and that is a very beautiful thing. But as a general, if you are really enthusiastic, you should commit it back. Now, by virtue of being open source, it has opened the doors, and it has and second thing is that the Hadoop became an umbrella for all other components also. They started supporting all other components such as HBase, which was based on a paper by Google again called Big Table, and Zookeeper, and all sort of those solutions they started building. And Hadoop became a big umbrella of components which solve these three problems, or generally big data problems. These three problems, as in, it should be reliable, it should be scalable, it should be distributed computing, right? These are the three characteristics of the product which lie under the umbrella of Hadoop. So Hadoop is generally a suite of tools, and we will be going through all of these tools plus two more tools such as Apache Storm and and Apache Storm and Zookeeper, and in addition to these components. All right. So Hadoop has got a file system that is the base of the whole game. Hadoop file system utilizes the native file systems to provide you a reliable, resilient file system using multiple computers. Okay, and how we will go into the details. And Hadoop file system is the main component on which everybody stands. HBase uses Hadoop file system. Flume imports the data into Hadoop file system. Scoop also imports the data from structured sources, and so on. So everybody, this is the base of the whole game. Okay, like with any operating system, the file system is the first thing they need to figure it out. Okay, all right. So are we on the same page? Excellent, excellent. Let's move on. So keep asking questions, and I'm looking for more questions, because if it becomes a one-way traffic, then you will lose your focus. So keep asking your questions, and I would love to answer them. Okay. There could be only two reasons why you don't have questions. First, you understood everything, or you understood nothing. All right. All right. So I'll go on. I'll make you ask questions. All right. Siva, the internals of HDFS are coming. Don't worry. And file system, Anjani, just give you a second and then you will understand. And so, what do we mean exactly by file system? File system is the crudest way of storing data onto the disk. Disk has got its own structure, such as it might be round, it could be any way, but giving it a logical form where we can write our text or our binary information without knowing how is it going to get stored physically, is something done by done by the native file system, such as NTFS, eh, DOS file system, eh, and I mean FAT32, FAT6, and those kind of file system. All right. While Hadoop file system also provides you a similar solution on top of the way native file system provided you a solution on top of the hardware, physical hard disk, so that you don't have to know nitty-gritties about the hard disk, right? And how to store, in which location it has to store the file name and all of that. It provides you a logical interface, human to the developers, so that they can write the data, okay, or to the programs, right? So that was native file system. On the similar line, Hadoop distributed file system provides you a very simple interface, so that under the hood it will store the data in the cluster without you being bothered about it. All right. So that is why it's called file system. Okay, okay. I see a lot of. Yes, I see. Apurva, I see your question. Okay. All right. Siva, I will answer your question quickly. And okay, I'll answer your quickly, Sumitra. Right, right. So Dave's question is, are there any Hadoop starter kit projects? There are many actually. Okay, and we will also provide you a simple starter kit so that you start working on it. All right. Right. So Apurv, you cannot see the questions of another other people. Only in the first session. From second session onwards, you will be able to see everybody's questions. And for some reason, these people from GoToWebinar don't provide that. All right. Now, now everybody is having the question about the HDFS. Before I answer everybody's question about HDFS, I'll come back later. I'll just give an introduction of what is HDFS. All right. So let's jump in. It's a simple problem statement. We all have been haggling with it for quite some time. Now, you have got 100 terabyte of requirement. Okay, how will you build such a storage? Okay, or let me put it in something which you can correlate. Say you are living in a society where there are some 2000 people living, and all 2000 people unanimously decided that they will build their movie store in the society itself, so that everybody can watch movies immediately and also can store the movies at the central place. Here I'm not promoting that you all should be pirating, but this is just for the example case. Okay, now, so if you are in a position that you have to build such a system which can provide 100 terabyte of storage, what will you do? How will you store 100 terabyte of data without saying that okay, we will use cloud or anything? How will you build this 100 terabyte of storage using existing file systems, and what will you do? Or before the cloud came into picture, how did people store 100 terabytes of data? That's what my question is, so that everybody in the network can watch the movies and store the movies into that storage. Okay, so the my reason of asking this question is so that I'm able to organically take you to what is HDFS and why do we need HDFS in first place. You will have all these answers, and in case if you are really inclined towards it, you might start thinking that I can build better than HDFS. All right, all right. So Sumitra is saying that, just a second. All right. So Sumitra's answer is store in multiple systems in different chunks and retrieve in parts. Excellent. Excellent. You are quite closer to the actual design. In a lot of hard disks connected together. Good. Good. So we'll come back to this design very quickly. That was Venkat's answer. Now, pre-cloud, I would probably partition the data or put A movies on one server, B movies on excellent. That was Dave Mattingling's answer, and that's a very brilliant answer. And probably I mean, I actually built in the same manner before before the cloud. Okay, so what he's saying that partition the data. Put movies starting with A on one server, movies starting with B on another, C on another, D on another, and so on till Z. Right? That is that. Yeah, that is how we actually did in pre-cloud time. Right? Good. Yes, Venkatesh, the access will be very slow unless a great algorithm is used. Right. Shivaji's answer is segregate the data on a particular characteristics like alphabetic order and store in different hard disk. Brilliant, brilliant. And yes, yes. Good, good. So anybody else, just give me, just shout out your suggestion, and I would love to. I mean, shout out as in type, and when you shout out and typing, don't type it in capitals, right? All right. So mount 1 terabyte of 100 instances on a single server and access them. Good, good. So most of the operating, I mean, the BIOS does not provide you to connect 100. Okay, okay. You are saying. So Siva's answer is mount 1 terabyte of 100 network file system instances on a single server and access it. Brilliant. So we got the answer, and this is how we actually did earlier before the pre-cloud era. We either built network attached storage or storage area networks. Both are similar in behavior in general, with the minor differences that are irrelevant right now. Now, if I have to build, what I will do is I'll buy 100 hard disk and attach those 100 hard disks to multiple computers and attach those computers to the network, and then mount these hard disks on on every computers in the network, so that on every computers there are remote drives visible, that these are the drives attached to my computer. Okay, although they will be remote, so every computer will have 99 pointers which are pointing to network drives and one is to local. And that's how I would build a uniform system which is catering to 100 terabyte of data. Now the problem would arise that if I have got a movie, should I put in drive 1, drive 2, drive 3, or drive 4, or 100? Where should I be putting this movie? So I'll have to partition the data, right? As most of you have brilliantly answered, right? Now there are challenges. So hope everybody got this design, right? Now what are the challenges do you see with this design? Quickly, quickly. Okay. What are the challenges do you see with this design? One is access issue, right? And backup issue. Okay. Excellent. Excellent. Thank you, Sivaji. And which data resides on what will be a problem? That was Siva's answer. W- What if, so Cletus, your question is that what if the file is too large, then where will we keep it? What if your file does not fit on drive 1? It has to fit on drive 2 also. Right, right. The main folder is bottleneck. Thank you, Sam. And network speed constraints. Excellent. Thank you, Vishal. Popular movies aren't any closer via cache. Excellent, Dave. That's a very good point. And now, no correlation between drive. Good, good, Pavan. And if multiple people want to access the same file, it becomes a problem. Thank you, Vishal. Brilliant, brilliant. Fragmentation, filtering the data. Good, 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 good. We have got a great set of answers, almost everything is answered. So these are the challenge which you just told. First is, what happens when drive 1 fails? So the general way we earlier did was we keep a backup of that drive on that particular computer, so that that drive fails, we do not lose the data. But what if the whole computer fails on which these drives are connected? Or what if these node which is running that, hosting the drive, has got software problems or operating system problems, virus problems? Or I have seen even the data centers where mice has eaten the cable, and a network cable, and this is quite common, and there's a fire on that particular data center, your data is lost, right? And fire is not very uncommon, right? So the failover and backups are really pathetic in our design. The design which I just gave would failed on this. Second, how would we distribute the data uniformly? And this sentence has multiple kinds of meanings. First, most of the movies start with the or a. And therefore, the way we had designed that we will put all the movies in this folder or in this computer starting with T, that whole schema will fail. Now we'll have to devise our own, you know, kind of an index saying this file is stored on this computer and so on. We'll have to build that kind of solution. Second meaning of distributing data is important. Other is, you got a big file which is not fitting onto drive 1 because drive 1 is already half full. So you got 80 GB Blu-ray movie, and drive 1 has got only 40 GB space left. Now that 40 GB space is actually wasted because we are trying to store 80 GB movie, right? And then that will spill over to drive 2 or whatever scheme you follow, right? So that is another problem. Now, is it the best value for money? We bought 1 terabyte hard disk. Maybe right now you can get 500 GB hard drives at a very cheaper cost. Okay. Or maybe you already have hard drives available in your organization lying around which are smaller in nature. Can your design tolerate so many small hard disks? What if we have 80 GB hard disk, 50 80 GB hard disk? Can you manage that? Answer is no, because this design will have to do a lot of shuffling, a lot of roaming around the network. And what if one fails and we will have to struggle with all of it? Okay, if we have 40 GB hard disk lying around, we can't use it because what if we have a Blu-ray that wouldn't fit into that hard disk, right? Now, increased accessibility, one of you pointed to that, the access problem. This is something which we, yeah, okay, yeah. Yes, Dave, that's a wrong kind of computer mouse I was talking about the mouse which the rat in the data centers. All right. Yes, that's another thing. So Ravinder has got one more point which I will add into these 5 lists. Thank you, Ravinder. If all servers are full and you have to add more hard disk, then can this design really scale up? We add one more computers to the network. Now we have to do a rebalancing of file because we'll have to change our scheme, the scheme which we had prepared. And therefore your scheme failed pathetically. So I'll add one more point here. Let me just take a note of it. Good. Right? And increasing accessibility is one thing which most of the people skip and avoid. And what does it mean? It means that a movie was released a few days back, the DVD was released few days back, and or we got a good print from somewhere. Now everybody wants to watch the same movie, or some actor's birthday is coming up today and everybody wants to watch that. It's a Independence Day and everybody wants to watch Gandhi, right? And therefore The moment accessibility increased, that network, that computer on which that movie is stored will get a hit. Okay, and that computer is overly crowded while others are resting. So that load is not balanced properly. The accessibility is not there. Because it's the same hard disk, it has to jump around and read the data for that particular person, and all the people are asking the same hard disk. Everybody will stay in the queue, and maybe the network chokes, right? So there are hundreds kinds of problems that would arise. Now, the answer to almost all these questions is HDFS, Hadoop Distributed File System. And how does it do it, right? So should we take a break now? Hi, so guys, I'm back and let me answer the questions which are pending. All right. So, besides the recording, will the slides be available? Yes, Dave. Recording as well as the slides will be sent to you in an email for the first session. So, you do not have to worry about taking the notes. Okay, and Subhas is saying that would like to see more use cases if possible. Yes, Subhas, the actually use cases I have covered in the more, but I have skipped it in favor of the time. Hi, Shrikant. So Shrikant has couple of questions from architecture. How do we exactly classify structured, unstructured data? Do structured data means we have a way of identifying the pattern in the data? And okay, that's a very good point. I think I think I skipped that part. I'll just go over that. Can the normal trace files, flat files, zip files we used for debugging be stored as? Yes. All right. Thank you, Shrikant. Those are very good questions. All right. If everybody is in, I can start. All right. So let me start. I hoping that everybody has come back because I run on very tight schedule. So it would be difficult for me to wait. Now, okay, so let me answer the first question Srikant has asked. Srikant's question is that how do we actually classify structured or unstructured data? So let me just go over this here. Right. So any data in which we know that these are the fields, this is the data type of the fields, and such as a relational database table or even an Excel sheet is a structured data. We know exact structure of it. While while file XML kind of file, which we know that there is a structure, but we don't know the data type of each value. It may be string, it may be date, it may be boolean, it may be int, which we will try to guess when we parse that XML file. In those all circumstances, we call it semi-structured, or a CSV file, for example, where we may not know the actual data type of each column that is considered as semi-structured, while unstructured data is something like a log file which does not have a proper field separator, or maybe unstructured data can be something like a video for which just doing a quick analytics will not be possible. We'll have to first figure out a way to convert this file into structured data such that we can do immediate analytics. Okay, so the translation from unstructured data to structured data is is something which requires a lot of effort, right? And all of this, because even if you have a huge Apache logs and you want to convert that into a database table, that might require you to actually use a lot of technique of distributed computing to pull Apache logs into your HBase kind of database. So all here I'm trying to portray that translation between structured to unstructured data itself is a big data problem, as well as definition of structured and unstructured data is very uh, subjective. All right, in general, whenever we know what are the fields inside our data, and the fields, when you describe what is a field, something of a smaller granular level with respect to the kind of analytics you are expecting to churn. All right, that is called the those are called the fields. And if you have good definition of the field, these are the column and what is the data type, whether it's int, long, boolean, date, or maybe complex data type containing other fields of various kinds of data types. In those cases, if we know all of this, then we call it structured data. And if we do not know some information, we know that okay, this is the field separator and this one is first field, this second field, but we don't know their data type right away. We'll have to figure that out. In those cases, we call it semi-structured. In case we don't know anything about a file, that what are the fields, how they're organized, we need to do a processing to figure that out, what are the fields. In those cases, we call it unstructured data. All right, so I hope I answered your question. Now, next question is, can the normal trace files, flat file, zip files we use for debugging be stored as big data? Is there any restriction for that type of big data storage? So there is no problem in storing any of these files on file system, right? On these HDFS kind of file system. The only thing is, since it's a network and there is a little bit more lag as compared to your NFS, when you say you have a small 10 kilobyte file that you can fairly afford to keep it on local, and just you need to keep a backup, right? You can keep the backup in that case. But if you have a smaller file and you need it immediately, then probably you would like it local. Otherwise, if you have lot of such small files and you need backup, you need to make them available to all other people, in those cases it would be preferable to move it to HDFS or any other similar system. All right, okay, that's a very good question, Parveen. So let me just describe what is admin node and then I'll answer your question. Okay, I'll so the question, even I'm not reading the question right now. Great, great, so we are ready now. So the answer to our problem of storage was HDFS. And how does HDFS do it? Basically, there are two kinds of nodes. One is called admin node, which stores only the basic information about your file. And the information on top of information is called metadata, the data on top of data. So the information about your file is called metadata. So admin node stores the metadata in the memory. All right. So admin node is the one which stores the only the metadata, such as when the file was created and other information. And now then there are another kind of nodes which are called data nodes. They are the workhorses. That's where your file will be stored. Okay. Now now so so it's a typical master slave architecture. There is one master, multiple nodes, while admin node just is keeping information. and the actual files are being divided into multiple data nodes. The way we had been talking earlier, we also had similar kind of structure in previous screen, but here there is far more to it. Now, data nodes store only a small file in small chunks. So if you have a 1 GB file, you go to admin node. When I say you means your representative, which is the file system driver or the command line. Okay? Because you will be asking file system driver, give me this file and save this file. That's the only objective you have with respect to HDFS. So when I'm referring to you is your driver. Okay, now this driver goes to the admin node, says, hey, I want to store this 1 GB file, and admin node says that okay, fine, go to these data nodes, divide your file into these small chunks and start storing. So each data node will be storing the file in smaller blocks. So the block size is typically 128 MB right now. Earlier it used to be 64 MB, right? So every file is divided into small chunks and stored on data nodes across the cluster. Okay, so that's a very simple way of saying it. Let me again clarify. So you had to store a file. You went to admin node and said, hey, I want to store this file. Admin node replies back to you saying, why don't you divide your file into a chunks of 128 MB each? Store the first chunk on data node 1, second chunk on data node 2, and so on, based on certain strategy, right? And that strategy basically makes sure that your data is fairly distributed. Okay, so the first copy generally stays closer to you, the first data node, and rest of the copy. Okay, so before I jump into that, so now we are clear that even no matter what file we have, we sliced it into small chunks. It helped in distributing your files. The problem which we raised earlier, even if our Blu-ray movie is 80 GB, the blocks will be smaller and a they will fit into the each data node. Okay, so it is like we have a big block of things to be pushed into a jar, to we cut it into small pieces and fit it into the jar. And in the same mechanism, this whole so the first thing they did was divided the files into small chunks, distributed them across network, and kept the metadata at a central place with admin node. Okay, so whenever you start writing, you inform the admin node that hey, I want to write this data. Admin node says okay, fine, you go and store the data at data nodes. Don't bother me. If I keep reading, if admin node keep reading your data, accepts the request of reading writing the file, then admin node is the bottleneck. Therefore admin node delegates all of this communication back to each data node. All right, now next point is replication, the backup and failure which we talked about. What if we stored a block on data node 1 and data node 1 went down? Or if there is an increased need of accessibility, more people are asking about the block 1, then data node 1 should not become the bottleneck. Okay, therefore there is a concept called replication. So every block you put is by default, let's keep it 3. 3 is the replication factor and can be configured per file as well as per for the whole storage. So every time you store a file, you can specify this much replication factor I want. And now based on this replication factor, number of your block is replicated, copied that many times onto other data nodes, and that's what makes it really resilient, right? So say you have so by default, let's just assume for time being it's 3. So each block is being copied 3 times. Okay, 3 times. So in case a data node goes down, we have a copy available in the network, and the instant admin node comes to know that this data node has gone down, all the blocks which got lost should be immediately should immediately recover their replication factor such that from the replication factor which was reduced to 2 should become again 3. Okay, so therefore it informs the data node saying data nodes 4 to start copying from data node 3 those lost blocks. Okay, similarly, the other role which is being played by the replication factor is rebalancing and distribution. So you added one more data node. Okay, so you added one more data node to the cluster, and that data node need to have one more, need to have the data, right? So all the data nodes will be informed to transfer some blocks to this newer system, and which blocks will be informed by admin node. So the rebalancing, the replication factor maintenance is actually done by the data transfer between the data nodes without admin node being bothered all the time, right? Right. So we talked about blocks, which is generally 128 MB. Every file is divided blocks. We talked about replication factor. We talked about rebalancing, and we talked about resilience also, where one data node goes down. So to maintain the replication factor, the data nodes are asked to transfer the data amongst themselves, specifically by admin node. All right. Now, second point is, okay, now, what if, as Parveen asked the question, that what if one this admin node goes down? What do we do then? Thankfully, earlier there used to be a concept called secondary name node. Secondary name node's duty was to keep a copy of this metadata. All right, to keep a copy of this metadata, which we are talking about. So let me just make few notes. All right. So in case of admin node, right? In case of admin node or name node, earlier we used to have secondary name node which used to also keep a copy of the metadata. And admin node keeps all the metadata into the memory. Okay. Why? Because the whole latency has to be dropped to 0 so that name node doesn't become the bottleneck, and for the consistency reasons name node has to be singular at a point of time. Therefore, what name node does is, first it keeps the backup of the metadata which is in the memory. Also, it keeps a copy of memory into the file system. We call it disk supported memory. So everything we push into memory, it gets mirror into the disk. Okay, so that is first step, which means in case name node goes down, we have the metadata in the file system. Second, there is a concept of secondary name node. There used to be something called secondary name node. The only problem with secondary name node was it only had transaction logs, and for transaction log recover, you have to build the memory from the transaction log. It used to take a little bit more time. Now few people did really good job and created something called backup name node. Okay, backup name node is an identical copy of name node running in the network in the cold manner. Nobody is talking to them. They are just running silently at their own. Okay, they are running silently at their own happily, right? So the backup name node is something a better solution than secondary name node, because secondary name node takes a lot of time to come to the life. Okay, backup name node is always ready and is done by guys at Huttonworks and few more companies, are done properly actually. So the moment your name node goes down, you swap it with the backup name node. All right. Also, the important thing to notice that admin name node is generally capped with a big RAM size, while data node is something which is smaller RAM, smaller CPU, but bigger disk. Okay, and these data nodes are generally not very costly. Although name node is little costlier because minimum amount of memory you need for running the name node is around 4 GB minimum. Okay, because you need to have that mode ready. All right. Now we have got, so I have answered both questions of Uma Praveen and Praveen. All right, let me go through the question. So Siva's point is that who does the replication? Replication is initiated by initial write. When you ask NameNode to write any file, NameNode tells you that you have to store this data on first node, and that data node will start copying in between to another one. Basically, okay, so first copy is written by you to the nearest one to yourself, and that replication will start happening between the data nodes itself. You don't have to do the replication. All right. So Anjani's question I have answered. What if admin nodes goes down? So where the replicated data is stored, that is Ravinder's question. Replicated data is actually stored just like blocks on the another data node. So one block exists at multiple places. Okay. Yes. Name node is nothing but admin node, name node. We are basically using those two aliases. How is the backup name node updated with the information from main name node? That's a very good question. Uh, so now that is done over the network. Name node keeps on informing and pushing the data in a pipe to the another service running in the network called backup name node. Okay, Anjani, let me again repeat. Okay, so you got your answer, Anjani, or should I repeat? So where does secondary name node reside? So secondary name node is up to you whether you want to keep it or not. But backup name node is also backup. Secondary name node exists generally on a different node than the one which is running name node. For obvious reason that in case this name node goes down, we have somebody to fall back to. Alright. So secondary name node or backup name node generally exists in the same network on a different rack, and taking the backup of this one. It's up to you where do you want to keep it in the network. But make sure you don't put the secondary node on the same machine. Okay. Each node has its own OS, have application running that determines what it needs. So each node may have any kind of OS, but all of these, when I say data node, admin node, or whatever, it essentially means I'm talking about a process, a Unix process, or a Windows process running in the background, listening on a network port. That's what it means. When I say data node, it's a normal computer running a extra process called Hadoop data node, which is listening to the network traffic and answering all your questions. And they have a predefined port, and name node knows which port and which machine number contains which data node. All right, that was Veerana's questions. So each node has same replicated data, or is it distributed uniformly? All right, that's a very good point. That is Nitesh's question. So yes, Nitesh, not necessarily each data node does not need to have the same replicated data. Okay, so your file may reside on 15 computers, different 15 computers, and their backup might reside on these 15 computers itself or maybe on another computers. All right. So that is something a scheme being managed by NameNode. Yes, I'm still on the core component slide. Wow. I've got a great set of candidates in this class who are having a really brilliant questions. Does it all also perform the task of resource allocation like NameNode, or simply stores the backup of NameNode metadata file? No, actually, till the point the secondary NameNode is running there, okay, it does not do any allocation. Probably you are, when you say it means secondary NameNode, backup NameNode, right? Probably you're talking about backup NameNode. Okay, so backup NameNode does not do any kind of resource allocation. It does not share that load of performing resource allocation. It just stays silently over there in the network. The role of figuring out the resource allocation is handled by NameNode by them itself. Awesome. So, right, like your general expectation, NameNode does not share the computation with others. Right now, NameNode makes sure that a file is not written by two people simultaneously by making sure that whenever you start the computation, you start writing to the file, because you went to NameNode, NameNode said that you came and you are probably writing to the file system. If you do not return to NameNode in correct time with saying I have done and I am committed the file, it does not make an entry with a confirmed one. It will discard your changes. Whatever blocks you wrote into the data nodes, they will be garbage collected after some time. All right. If you do not confirm to name node after you have finished, and you means the driver goes to name node, stores the data on data node, goes back to the name node saying I'm done, and then the name node starts the process of backing it up. All right. So this is what the general general architecture of HDFS looks like to you. All right, we'll go into more details of HDFS and MapReduce in the second slide also, but here is the another diagram which shows you that name node, same whatever we have discussed, the client came to you, the replication is happening between the data nodes, they are not, it's not bothering you. Client talks to name node, starts writing directly to the data nodes, and then commits to the name node. Name node is keeping this kind of metadata. All right. So name node is we all know all of this. All right. So name node keeps this kind of data. You can see the file name, number of replicas. So number of replicas generally is 3. R is 3 by default, unless you override while writing to HDFS. Okay. And which parts, how many parts are there of a file, which all nodes, data nodes are handling that part. And all of this information is handled by NameNode. And one more thing I forgot to tell you, that since NameNode is heavily RAM intensive, it, it requires a bigger RAM. In case it figures out the RAM is going scarce, what it will do is, what it will do is it will start increasing, the block size which is fixed by default. It will start increasing the block size to reduce the metadata, and hence it'll have the lesser metadata and still it will run happily. Okay, those are the clever optimizations done on NameNode, and they keep on changing the strategy in one release after another. Okay, so you don't have to hang on to these words all the time. So how much time NameNode waits? Where is it configured? And is this different for different tasks? No. So these are standard timeout things which are configured by default. And in case your network really network really poor, in those cases you can configure NameNode to have a different timeouts. All right, and these are configurable things. So configuration is generally stored in etc Hadoop and one folder over there at every machines. So Anjani's point is, in case the name node goes down, then the backup node has to do the resource allocation. Yes, you are right. So the basically the backup node which we are talking about, it has a name node instance, right? It has a name node instance. It's just that it was silent. So the moment it is swapped to hot, it will have that one. It will behave exactly like name node. So what if we don't have a backup name node? That is Nitish's question. Hadoop will not complain about it. Okay. But as a matter of practice, you should keep a backup name node. Okay. Because in case your, I mean, if you don't have a backup name node, still it's fine, because as you can see that name node keeps here records transaction log in the file system, right? Then in case it goes down, you might have to copy this transaction log somehow from this machine to another and start over there in case this machine is not booting up. So there will be a lag in the whole game. All right. But you are I mean, you are sitting on a, if you do not have a backup name node, then you are, it's not great idea. All right. Now moving on. So we talked about HDFS in a very general way, right? We talked about HDFS in general way. We'll go over our HDFS cluster, which is there in the second session onwards, and how to log in and all is will be detailed to you in the document. All right. I will. All right. Now, now the second part. This was all about file system. So we built a brilliant. I mean, Hadoop has built a brilliant file system where you can keep files, and it doesn't matter whether one node went down or one node got corrupted. It doesn't matter to you. Okay, as long as your name node is running fine, you have a backup name node, everything is fine. Okay, at every moment, I mean, also these file system is append only file system. Okay, you do not edit a file, it keeps on appending to a file. In case you are deleting it, it just the name node removes the entry of it and then garbage collect the information later on. All right. So right, as I told you, you can delete the data by informing from the system. It's not a problem. The only thing is when you are adding a file, uh, creating a new file, generally it is appended to the previous one, and you have a history of the things. Okay. All right. So Chandra's question is the data keep accumulates in data node, or can we you can clean up the data? Because data node for you don't have to touch the data node. In the file system, it is clearly visible like a folder structure. If you delete a file, it will be removed. Okay. Unlike SVN, it won't keep a history of this one. What if there is no space left, no space for replication in case of failure? All right. Okay. Okay. So, okay, let me try to understand Siva's question. Siva says that what if there is no space for replication in case of failure? Okay. It'll give you an error saying that replication failed. Okay. And while it is taking accepting the information from you, taking a file, it has also figured out that replication is possible. only then only then it takes your transaction. Otherwise, it has name node has figured out that there is no space left for replication, and you are asking for a replication factor of 4, and it doesn't have a space that time. It will give you error then and there. All right. So Madhav's question is, the moment we add a data node to Hadoop cluster, does Hadoop start redistributing its existing file on new data node, or it will wait for next file add operation on Hadoop cluster? So the moment we add a data node on a Hadoop cluster, we have to inform the name node that you have got one more data node, and that very instant it will start redistributing it. Okay, because you have to inform the name node that you have got one more file to handle. All right, so moving on, we are talking now, we discussed about the storage part of data handling, and that is the, you know, the oxygen of the game. Okay, where the whole data will survive. Now the Hadoop distributed file system is something which has to be so resilient that everybody, and so resilient and so cheaply available. And even if your organization have not figured out right now that what are they going to do with the big data, the general strategy which I recommend to everybody is to start having a small HDFS cluster. Okay, and start pushing the data. Now as people know that, okay, we have got 10 terabyte of disk available for us. Okay, so developers tend to start creating the proper logs, more events, and hence after some time you will have lot of data to do the analytics. Okay, so the first step in case of an organization is to build a HDFS cluster properly. So do we need to reboot Hadoop when we add data node? No. You don't even need to restart a name node to do that. All you need to do is you just add the configuration, and it will load that configuration file immediately, and then start functioning with the newer data set. Or it provides you a command line to add data nodes. All right. Any other questions? Good, good. So let's talk about something called computation. And this is very, very important. And we have got good amount of time at hand. All right. So have you ever tried thinking about how do you sort data? So whenever you create index on a database table, under the hood, it is going to it is going to sort the data in that particular column. Creating an index means sorting the data, right? Now, have you thought, if you have 1 terabyte of data, which means 10 billion names containing 100 characters each, how are you going to order this data? How are you going to sort this data? And say you know the commands, you know the sort command in Unix, that it sorts the data. What is your gut feel that how much time will it take to actually sort the data? Sort command has got minus s as a argument, in which you can specify that sort my data by creating this much, by consuming only this much of memory, and it will do all of it for you. Now give me a number. Okay, so give me a number of seconds or minutes. How much time will it take for a computer to sort 1 terabyte of data? And imagine that 1 terabyte data is stored on solid state hard drive. And my question to you is, will it matter to have solid state hard drive or normal hard drive? Of course it will matter, right? Because maximum time will go in reading and writing data from the disk. And RAM size is 2 GB, which means you'll have to read the data in 2 GB chunks and then try to sort it. And then whatever portions, whatever parts of the file you have sorted, you slice the whole 1 terabyte data into 2 GB chunks each. And now you are sorting that 2 GB chunk independently and then merging that. Merging sorted data to produce sorted result is far easier than sorting a huge data. All right, so what do you think, how much time will it take to sort? When I say sort, means ordering the data in increasing or decreasing manner, and here we have 10 billion strings, each containing 100 characters. How much time do you think will it take? So is the question clear to you? Just give a rough estimate, and to be honest with you, I could not estimate it, so I did run the actual test. Because saying 1 terabyte data sounds really cool and sounds like easy thing, but when you get down to the level that, hey, I need to order this data, I need to do the minimal amount of processing. Say out of 100, out of 10 billion names, I have to find out what are the what are the top 100 names if you order them alphabetically, right? In those cases you have to order the data in order to get this basic analytics, right? Now how do you do it? How much time do you think it will take? Just give a number. Even if you think it's 100 times wrong, it's okay. So algorithm, let's say we call it a merge sort, okay, or you can say it a disk sort. We are doing it partly in the disk sort, or you can also say it a we call it a network sort, basically keeping the data in the remote and then reading and sorting the data. So whatever algorithm you can think is fastest, you use that algorithm. Okay, what is the fastest way? How much time the fastest algorithm might take? All right, just give me a number. Give me a number. Anybody? Will it take 1 minute, 1 hour, 1 day, 1 month, or 1 year? Just quick, just quick. First answer and I'll move. All right, I think yes, somebody raised a hand. Yes, Sri. Okay, okay. Are doing the computation. So the Ravinder, the question is, how much time do you think it will take to sort 1 terabyte data? 1 terabyte here means 10 billion names containing 100 characters each, and you have got 1 gigahertz processor and 2 GB RAM. Okay. So disk speed is your disk speed. Very good point, actually, Parveen. Parveen says that it depends on the disk speed. Yes. And this I realized after actually running it. The disk was the bottleneck. It was not the RAM or it was not the CPU. Even though I had a sufficiently sized RAM, the disk was the bottleneck deciding factor. So here we are talking about solid state hard drive, which is around 1,000 times faster than the disk, way faster than the hard disk SSD. Okay, so Ambu says we may get the memory overflow message. Yes, we will get memory overflow, but we'll only split it. We'll split it into parts such that memory can be handled. Hours or days. Okay, okay. So this is the best I could do after using few terabyte hard disk, a few SSDs for solid state hard drives containing this 1 terabyte data. I could not go beyond 5 hours. All right, and so it took me 5 hours. Now the problem is that we would need a faster sorting algorithm. We would need a faster response time. 5 hours is not good enough when we are dealing with 1 terabyte data. Tomorrow we might have a need of 200 terabyte churning. The way I was describing you 200 terabyte data in a recommendation engine. So we might have a 10 terabyte need. This 5 hours will not linearly increase with the disk. It might be far more than the linear one, right? If we have 5 terabytes, which it does not mean that it will take 25 hours, it might take far more than that. And third problem with this is that we will have to sort more often, which means that we need faster sorting, we need we might have to sort bigger data, and we have to do it more often. And this is exactly the basic problem of computing is, right? If you think about your SQL query, creating an index, whenever you do a where clause, it generally looks up in the index, and an index is nothing but a sorting. Similarly, when you join two data sets using a join clause in SQL, you are joining two data sets on various parameters, and joining is nothing but uh, you sort both the data sets, data sets, and then try to find common in those, right? Intersect those data sets, and that is very much accelerated if the data is sorted, right? And therefore this sorting is very important game. Similarly, when you do group by is nothing but a sorting exercise. Sorting as in ordering the data, group by this. And when you have to group the data, we have to bring all the values of a column together which are identical, right? So group by is a sorting. So therefore the sorting is the holy grail of any computing, and any graph search, and most of the problems can be broken down into sorting. We will discuss this in detail when we go into MapReduce. And if you look at closely, the MapReduce itself is a grand sorting engine which sorts the data of very huge size using lot of computers. And we will go into the details of how does it sort it. Okay. Now, sorting becomes such a most important problem in the computing that there is a sorting benchmark.org in which all big organizations keep on competing every year, and Google and Hadoop has been winners couple of times. Last time Google reported that they were able to sort 10 petabyte of data, and petabyte is 1024 times 1 terabyte. Okay, 10 petabyte data in 6.5 hours on 8,000 computers. Okay, so this is the fastest or the biggest data people have been able to reach. So remember that most of the distributed computing we say at the heart of most of the distributed computing lies the sorting algorithms being done on multiple computers. Okay, most of the processing, whenever we say processing, it means generally a sorting in the backend. But sorting is not the only thing that we do in the processing. If you think about graph search and all graph algorithms or other algorithms, there are more things in processing than sorting. But most of the problems can be broken down into sorting. All right. Now we have got something called compute engine. Compute engine, this is now called yarn. It was known as MapReduce earlier. Now MapReduce is just a small paradigm, but we'll use it interchangeably. But let's jump in. Okay, so whenever we ask Hadoop to do anything, to do any work, let's say we ask Hadoop to sort this data, whatever we have asked. Okay, now what it will do is, under the hood, this is the basics of the job distribution. This is also called yarn, yet another resource negotiator. Yet, so yarn job is, so whenever you give a job to yarn, it has got two kinds of node. First one is job tracker. Job tracker is exactly like your name node, which is a master and does nothing but keeping the record of who is doing what. And task tracker is the real workhorse, which does the real job. Okay, and the general strategy is to keep task tracker and data node closer. Again, data node, task tracker, job tracker, admin node, or name node, or backup node, all of these things are network running daemons, or all of these are processes which are running on each computer and listening on a particular port. All right, so this is what it is. So you ask any work to job tracker will delegate the task to task trackers will finish the job and report back to the job tracker that they are done. And in case task tracker notices that any of the so all the task trackers will finish the work, inform job tracker that they are done, and then move ahead. All right. And once all the task trackers are finished, job tracker will report back to you saying, I am done. Okay. And all of this happens in a batch processing. You give job tracker your job tracker gives you a tracking URL saying that you can track my status at that URL. You don't have to wait for me to finish. You have to poll this URL to see the status of your job. Okay, and job tracker in the back end gives the task tracker to gives the task to each task trackers, and each task tracker does the work and reports back to job tracker. Now big question arises that how do you distribute the job? How, if you're processing on task tracker 1 depends on task tracker 2, how does it do it? The simple straight answer is it doesn't do it. Okay, it doesn't do that kind of processing. Always the kind of solutions are built on top of job tracker, the kind of assignments we give to job tracker, we tell him that this is how you will divide the processing very clearly. Okay, that is the most important thing. And the first kind of processing is done in the form of maps and reduces. We'll talk about it very immediately. Now, the other thing which you should remember is whenever we are giving job tracker a task, it can use something called data locality optimization. What does that jargon means? It means that when it is doing the computing, it should send the computing to the nodes containing the data. So you ask job tracker that, hey, I want to sort this file. Okay. Now you ask the job tracker, hey, I want to sort this file. Can you do it for me? And job tracker takes your request and figures out where all the blocks of this file are located. Okay. And whenever you're giving job tracker, you have to give some file. I mean, you can not have to, you can give the file to job tracker saying this is the file I am trying to process. Now job tracker figures out that, hey, this file is located on these data nodes. Job tracker figures out by asking NameNode, which means job tracker knows about NameNode. Job tracker knows about its task trackers, right? So job tracker asks NameNode ki, hey, do you know which all computers contain this file? It says that these data nodes which are running on these ports, you should get your file from there. And based on that, based on those data nodes, it figures out which task tracker is located near to those data nodes. Okay. And you can, right now you can think of data locality optimization like finding similar closest IP addresses. If the last digits are matching, which means those, I mean, if you have given two IP addresses and you have to find out which machine, how far are they, or given three IP addresses and you have to find out which two IP addresses are closer, you can start comparing from the right hand side. If the last digits of the, I mean, how many? I mean, if the last digits of two IP addresses are same, I mean similar, which means they are on the same closer as compared to if the first digits on the left hand side, which are basically if you have got 192.168.1.2 and 192.168.1.3 and you have got 192.168.2 dot something, right? So the third subnet, third number from the left hand side, if that is differing, that means you have got that node farther. Okay, let me just explain. So so data locality, the way Hadoop does it, say you have got one IP address this, other is this, and other is this, right? So what do you think, which are closer computers, this and this, or this and this? Which one is closest? Quickly, quickly. First two, perfect, perfect, right? So in the similar manner, it figures out, which are the computers located nearby. Okay, and this mapping IP address and the real name can be done by you, but by default, IP address is considered as the data locality optimization. So, given IP addresses of data nodes and and the task trackers, it can figure out which task trackers are running closer to the data nodes where my file is located, and hence it makes complete logical sense to send your computing to the nodes containing those blocks which you want to process, right? Yes, you are right, Sivaji, and good. Now, so that's a very important aspect. Since all of data is going to be big, when you are churning 200 terabyte data, is does not make any sense to bring the data to one computer, read it, and compute it. As we talked earlier, also the fourth pillar of the computing is network, and this is the way Hadoop tries to optimize the network performance by sending computing to the data rather than bringing the data to the computing. Okay, so whatever logic you have written, it is distributed to all task trackers, and only those task trackers which are closest to your data, unless those task trackers are completely busy. Okay, if those task trackers are completely busy, the computation will be sent to the next task tracker which is free but closer to our data node containing the blocks of the file which we are trying to process. right? So here, Sivaji, let me explain again. He's saying, can you explain about bringing computing nearer to the data? So here, when we are sending our program to task tracker to execute, that program is basically moving from job tracker to task tracker. Unlike our olden days where we used to bring data, that your code used to read data from remote, then process it and put it back, right? And that has been turned upside down by sending the computing to task tracker which is near to the data or on the same computer as the data node. Okay, if the same computer, then it's well and good. If it's not, let it be on the same rack. If it's not on the same rack, let it be on the same data center. If it's not on the same data center, it should be I mean in the closer geographies or some way or the other. All right. And the other way other systems such as MongoDB tries to optimize the data locality is by the way of ping responses. All computers keep on pinging to each other, figure out which one is responding faster and consider that computer as closest. That kind of optimization has not been done by Hadoop because that requires a lot of noise in the network of ping. The ping create a lot of noise, so they, as per the design, they have chosen a static way of defining the network topology. You can define your own topology instead of having this IP based topology. Okay, and based on that topology it will keep on doing that. Okay, so we talked about few things. First, every task is divided onto task trackers, and each task tracker finish and give response back to job tracker, and each task is sent. If you are performing an analysis of a file which is located on HDFS, the only those task trackers are utilized which are closer to the data, right? Now, next point is that next point is that when when a task tracker fails, job tracker keeps on pinging task tracker and asking what's the status. In case a task tracker fails, in those circumstances, same computing is handed over to another machine and the results of the first one is discarded. Okay. And while sending the same computing to another, it might likely send it to the replicated block which is there in the network. Okay. All right, so I hope I have been able to explain job tracker, task tracker, the yarn framework. And when we say yarn is exactly this. Yarn is negotiating resources with, yarn means yet another resource locator. And this is another diagram representing it. So job tracker sends work to all the task tracker performs work and give back the results. And under the hood there are input files. User has submitted its job, copied the data to HDFS, and this client goes to HDFS and then submits job to the job tracker. Job tracker further creates maps and reduces. We will go into the details of map and reduce. Map and reduces is one way, it's just one way of performing the job. It's the same thing with whatever we have described earlier. Okay, right? So job tracker maintains a job queue of whosoever is doing what, which task tracker is doing what. In case a task tracker does not respond in timely fashion, it does a timeout again, and by the way of heartbeats, it knows that the node is down and there's no point in waiting and move on. All right, and then it basically assigns the same task to another. Okay. So this is a very simple diagram. This explains better. So do we have any questions with respect to this distribution of work, job tracker, task tracker? Okay, we'll go into more details of Yarn because Yarn has multiple other services which need to be addressed. right? So any other questions, or should I move on? All right, all right. Okay. So is everybody awake, or have I put to the sleep? Have I put you to the sleep? Great. At least Vishal is awake. Okay. Yes, Ravinder, this video will be available to you. No worries. All right. So everybody is awake. Excellent. Excellent. Now, it's the same thing which is described earlier. Now I will take a brief, maybe 2 minutes to describe what is MapReduce. So we talked about blocks on each node. So look at this. I don't know what color it is. Probably it's green color. Split 0, split 1, split 2. Okay. Think about each split as each block on HDFS. So each data node 1, data node 2, data node 3, containing 3 splits of a file. Okay. Now you wanted to do some processing such as counting words. You want to count words in a 200 terabytes. All right. Now you wrote a MapReduce job to do it. What does it mean by MapReduce jobs? So out of MapReduce, you have to code. Okay. You have to write a map function which takes your input file or lines from the input file, and as a result it gives out key value pairs. Okay, key and the value. So in the counting words, your map job will be giving key as the word and value as numeric 1 to 3, numeric 1, right? As this word has been encountered once. For each word, that's what the map will do. Just be with me. I'll go over this diagram twice. So we have got 3 data nodes here. We asked the job tracker that, hey, we want to count the words. All right. And this is my map job. This is my reduce job. And by the way of map reduce paradigm, it has sent your map function to each data node for processing, right? On task tracker, when we said we are sending the computing, it's actually sending your code which was there defined that this is my function called map. Okay, mapper or map, I'll be using these terms interchangeably. So our mapper, that code will be sent to each task tracker, and on that task, and by the virtue of that mapper, it will spit out, it will give out keys and values. And in our example, key is the word and value is numeric 1. Okay, so that's the job of the map. So map took line by line each chunk and converted that into key 1 value, key 2 value, key 3 value, or word and then 1, word 2 then 1, and so on, right? So that's all map did. And this is happening, this translation of lines into key value pair is happening on each task tracker, or each task tracker which is running on the data node, right? Data node is something which is containing your file. The chunk, this block is being there. This block split 0 is on that on the data node, and on the data node is running a task tracker which is reading that file and line by line converting into key value pairs. And these key value pairs are right now, this key value pair as a result of map reduce are actually on the same file system, right? And once it has done that, MapReduce logic runs sorting on each node. Okay, it runs sorting on each node group such that all keys on a single node are sorted. Okay, and as a merge exercise, the data from all of these nodes, all the key value pairs your map has generated, which are sorted in itself by each node, will be merged on a separate node or on one of these nodes. But for now, let's assume that it's on a different node, right? So it will take all of these key value pairs from each of these three nodes and merge it. And remember, merging merging a sorted data is far more easier. You can visualize, you can think of three queues in which people are standing in their ascending order of the heights, and you have to merge these three people. Imagine that you have got three lines in which there are people who are standing such that the second person is taller than the first person and third person is taller than the second person, and so on, right? You've got three such queues or three such lines, and you are asked to merge these. So you will do very simply, you will stand in front of the, you will just make three queues in front of you. You'll go to the front means the shortest person in the queue, and start picking the, out of three queues, whosoever is shorter, you start picking that one and start forming third line, right? You start forming the third line, right? So therefore it's quite straightforward. The complexity of merging the three lines is actually of the order of n, right? And therefore, I mean, it's actually n log m. Log m is number of queues you have got. If you got three, that means the complexity will be number of people n into log of 3, right? We'll go into the details. If you have a question about this merging, I can go into the details in a separate session, all right? Or if you want to discuss the algorithms which we use, I can have a separate session for only those people. And that will be like a complementary session, right? So when we merge, the way we have merged the three queues just now by standing in front of the queues and picking up the shortest person out of the queue, similarly merging here only takes a, and this is in place merging, which means out of three queues we are just putting the people into a single one. We are not taking any extra third, fourth line. Okay. So that's called in place merging. So when the merging is happening, so data from two of the data nodes is going to the first one and getting merged. So this is actually happening on one of these three nodes. Just for the pictorial reasons, I have drawn it separately. But to reduce the traffic to one third, it's done it that way. All right. 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 Now, Now, after this merging is done, merging means now your data, the words, all words are sorted together, and grouping these words such that all the words are there and all the values of each word, which is 1 comma 1 comma 1 and so on, is grouped together after merging. So after merging, after sorting, grouping is a very simple game, right? Because all you have to do is go from the top, keep on going until you encounter a newer value, and then group all those values, keep collecting. Once you have aggregate, once it has formed the groups of all the values together for each key, it gives out to the reduce, and reduce is your function, which might be doing an average of all the values for a key, which might be doing summation of all the values for a key, and so on. In our example, each word is the key, and value is 1 comma 1 comma 1 comma 1, number of times that word has been encountered. And if we are looking for how many times a word is coming in, we'll just count all these ones, which means sum all these values called ones, and then say that this word has come this many times. So the way you write a reduce function is, you are given a word, a key, and an array of values, and it's up to you what you want to do with the values, whether you sum them, you average them, you do a standard mean deviation, or you do a root mean square value. It's up to you. Okay. So reduce function and map function is coded by you, and rest of the game, sorting, merging, grouping, and then and then splitting, is everything done by Hadoop for you. Okay. So a complex thing like word count, which is happening on 10,000 computers, all you did was wrote two lines of code. First one to break each line into words, each line into word comma one, and then you write another piece of code called reduce, which did all it did was summed up the values into and return the value. All it did was sum my array. That's all right. So that is called MapReduce paradigm, and this MapReduce is run on top of yarn. And similar to MapReduce, there are other computations such as Spark and Giraffe and other ones. So there are multiple ways of computations. Now I'll just describe the other things. Now every time for each small task, you cannot keep on writing MapReduce job. The way we counted words, we had to write the code, right? Now, most of such tasks used to be done very easily with SQL. So people actually wrote Hive kind of engines which accept SQL as an input and and do all the MapReduce job for you. Hive writes code for you. Okay, Hive converts every SQL query into MapReduce tasks. Okay, and we will discuss and you will understand how can you actually convert every problem of SQL into MapReduce, right? After some time, when people realized that Hive was actually, I mean, the SQL was not meant for the big data. SQL was not meant for a parallel processing. Therefore, people devised a language called Pig Latin at Yahoo. Okay, so uh, so Pig Latin is basically a parallel computing which runs on multiple computers, right? Pig Latin is a very simplified SQL language, SQL like language. It's not like SQL, but it's similar to SQL but far more flexible, powerful, and easy to learn. All the people who come from DBA background, they start preferring our Pig Latin over their own SQL. Okay, so Pig Latin is one very beautiful language similar to SQL, which is to overcome shortcomings of SQL in case of distributed processing. And then you have got Mahout. Mahout is the magician in the game. It's basically a library of algorithms. And when I talked about clustering, when I talked about recommendations, it's a single line thing. When you use Mahout, all you need to do is format your data in which that algorithm is expecting and then use that algorithm. Mahout is a library of functions, right? Just like another Java library. And and then you have Flume and Scoop. Flume helps you importing distributedly your bulk data from things like Apache and other channels. So generally, if you have a lot of Apache logs and a lot of hundreds of servers running, you would like to distributedly push the data onto each data node, and that's done by Flume, right? And for structured data, if you have SQLs in your data center, some of the data you might want to keep on pushing from SQL to HBase. HBase is one database I forgot to tell. HBase is for the cases when you have billions of rows and millions of columns, hundreds of millions of columns. So if you have that kind of need, you use HBase, and for frequent write needs, you will prefer to use HBase. Okay, so if you have to push the relational data from anywhere else to NoSQL called HBase, you will use Scoop for doing that. It does back and forth to, if you have CSV file, you can push that CSV file from HDFS to your MySQL and vice versa. Similarly, you can take MySQL table and push it to HBase table using Scoop, and this all is done using distributed computing. Okay, so these are the beautiful parts of Flume and Scoop. All of these are designed bottom up with scalability in the mindset. And all of these generally had been using MapReduce paradigm to do the computation. Including Flume and Scoop, they use MapReduce to do distributedly pushing the data to your HDFS and HBase. Okay, and now when you have so many components, some part is being done in Flume, Scoop, some part is done in HBase, some part is done in Hive, and then you are doing Mahout or Pig Latin, right? Now you have to create a workflow, and that workflow is Oozie. Oozie, you can think like if you have used Ant or you have used Make, okay, you have used Make or Ant or Maven. All of they are basically storyboarding your your process. Process 1 happens after process 2, then happens process 3. All of this is done using Oozie, and every job at Oozie can be triggered by human intervention or can be time based. So that's all is the ecosystem. We'll be talking about two more components in detail, called one is Zookeeper. Okay, and Zookeeper does not run on HDFS, but it runs for higher throughput in any network. Okay, and the storm we will be talking about in this whole sessions. So there are 11 sessions, and we will go into the details of each of these components to a decent level, so that you have an understand working knowledge of each of these components, and how can you convert your whole project into a series of these components. Okay, all right, so I am done. Let me answer your questions. So Subhas is saying would like to attend the algorithm session you mentioned about. Yes, I would love to do that. Let me plan that. Okay, and just drop me an email so that I put you onto a subscription list and inform you. I assume when MapReduce is in progress, it is necessary to stop data loading process. Is it right? So whatever data is available in for MapReduce, it will start reading that data. Okay, so it's not necessary to stop the data loading process. So Ravinder is asking command line Java Python is must. So I'll also demonstrate in the whole process that MapReduce is basically can be done using local binary files, right? And you can also do it in Python other than Java. All right. Okay. So Vishal's point is, if HBase is database for Hadoop, then what is stored in HDFS? So your question, let me rephrase your question in normal terms. If we have file system like NTFS or DOS FAT32, why did we need Microsoft SQL? So am I able to answer your question, Vishal? So basically, when you have to just store all the files, then you put it in HDFS, it distributes, and HBase itself stores its files into blocks on HDFS. And HBase gives you a key value pair kind of interface where you can do a fast read write. Now Chandra's question is, I need to extract data from Oracle DB every day and write to text files close to 100 million records. Currently, using Spring Batch with partition concept, it takes around 2 hours. Is Storm better or Hadoop better? Okay, okay. So I need to understand more about this process. And here probably your Oracle and the disk will be the bottleneck as compared to the Hadoop or Apache Storm. Because it will be the network which will hurt you badly. Yeah. So I need to go into the details. Let's discuss it offline. It's a very good, interesting problem. Okay. Ravinder, just drop me an email if you are interested in algorithm. Algorithms, basically, I will cover a network sorting algorithm, which will basically I mean, it won't be too difficult, and I'll just take 1 hour session for that. So Venkatesh is asking, you spoke of a Kickstarter package. So we will have that in our second sessions. Okay, we'll give you the detail. What is Spark? Spark is similar to MapReduce. Right now we created maps and reduces. Similar that in Spark you write a smaller programming language in Spark itself, and then you distribute your processing similar to MapReduce. I'll go into the details. We'll devote one full session onto Spark. Okay. So what are the prerequisites to learn Hadoop? So prerequisites are you should have some programming experience in any language, even if you did programming 20 years ago. So Ravinder, drop me an email at sandeep at knowbigdata.com and I'll get back to you because these question and answers get lost. Is there a way I can test it on a single computer? Yes, definitely, Venkatesh. What you can do is we guide you to install the whole virtual machine as well as we give you the access to our cloud labs, and then you can start using it. There are virtual machines available from Hortonworks and Cloudera. You can try those. All right. So we can do operations directly on HDFS files or they need to be processed. So HBase is optional completely, Vishal. And while HDFS files are mandatory because HBase anyway keeps that. So we can do operations directly on HDFS files or they need to be processed and stored. Not really. It's completely, absolutely up to you. It's completely, absolutely up to you whether you want to use HBase or not. HBase should be used when you have, really, really big kind of a table structure. Meaning, if you have billions of rows or millions by millions rows and millions column, then you should be going for HBase. So, to do MapReducer, which level Java I need to learn, mid level or else. So to do MapReduce, you don't need a very detailed understanding of Java. Having Java is a good point. That is why we will talk about how to do MapReduce using even simple commands without writing a single line of code. Okay, because MapReduce is a paradigm which makes you learn how to break down your problem statement into maps and reduces, and that can be done in any programming language. All right. So Subhas's question is, when will the next session is happening tomorrow, but for that you will have to enroll for our classes, and you can enroll to this class going to the website. That is Subhas's question. Yes. So Pavan is asking, if I want to enter into real time with your training, is it possible? Yes, it is possible. We have different kind of projects. So Pavan, yes, you are strong. If you are strong in C, C++, Oracle, and database, you should definitely be able to handle almost the whole game. Is virtual machine mandatory, or can I run on Windows 7 with Eclipse? So see, the thing is, because data node, name node, all of this needs to be installed, it would take a considerable amount of time to configure that on Windows 7, which has been possible actually. But the easiest way to have the virtual machine, or in case you are signing up for the full course with us, you can use our cloud labs immediately without installing anything. Is it recommended to use HBase for frequent updates and inserts like MySQL? Is it recommended to use HBase for frequent updates and inserts like yes. So if you have very frequent updates, you should go for HBase provided you have huge data. Otherwise, keep on using a Cassandra or some other smaller database, or you be happy with your MySQL. Okay, if your data is smaller. HBase guys themselves say that if your data is smaller, below a billion rows, then don't get into the hassles of HBase. So Pavan's question is, will any of these like Pig, Hive, Mahout are all required or anyone? So Pig and Hive, you can choose any one of those. Okay. While Mahout is a different ball game altogether. Mahout is a machine learning. So labs is basically online. We will go into the hands-on with the labs in the second session. Apurv. All right. Cloud labs are accessible even after trainings for 15 more days, and then we generally revoke the access. But in case you are interested in using our cloud labs, just inform us upfront so that we can do our capacity planning. So Nitish's question is that will you be explaining how to set up Hadoop architecture? So that I will take a complimentary session because this one is a sort of a developer course, and that anyway I'm planning to have a complimentary session for all the people on how to set up Hadoop in a in your data center. Okay. Can we have one node on Windows 7 and other node on Ubuntu? That's a very interesting question and very intriguing. So this was not possible few up to uh, few months earlier. Now Hortonworks has given out their HD insights on Windows, which means one node can have Windows and other node can have Ubuntu. Okay. But when you are running MapReduce, your Python streaming jobs will give an error on Windows, while your Java code will run smoothly. Okay, because you can also ask in MapReduce that execute this command, and when you make a system call, those calls will fail if you have a different kind of nodes. All right. Yes, Nitish. So in case you want to set up, well, I'm planning to have a separate session for all the people in which I'll help you out. Will make with making you understand step by step how to set up Hadoop. Okay, in a data center. Pavan is a researcher in data warehousing. Interesting. I would love to stay in touch with you, Pavan, and you also stay in touch. So when I saying not through VM, what will be the minimum number of servers needed to implement Hadoop? Will it be one main server and two data node? Yes, actually minimum servers would be two minimum because on one node you can put NameNode, on other node you can put task tracker and data node, right? So two servers are good enough to start with, and then you keep on adding the data nodes. All right. Okay. Now I wanted to integrate indexing with the uncertain handling data. Okay. Yes. Actually, those things you should be able to figure out once you have understood these components, right? Uh, Like, um, like for example, Pig or Hive or HBase or MapReduce. Mostly by the end of time, you will finish MapReduce. Most of the concepts with respect to, say indexing, as Pavan is pointing out, will he be able to do uh, integrate indexing with certain uncertain handling of data? You should be able to figure that out by the end of MapReduce. And if not, we will work together and we'll discuss in detail what you're looking for. No worries, okay? Even if you're not taking the full session, do let me know. If you want a discussion, I can have the discussion with you. What kind of things you're looking for in the research. All right. So you can register the session from a website. So Twitter handle is I know big data, and that Twitter handle is fairly popular. Are there any other languages for big data apart from Hadoop? So there are multiple other frameworks for handling big data. Even MongoDB and Cassandra, they let you handle. The only challenge with other things is none of them is a complete suite of components. Some only let you put in data in that format, but most complete out of all is probably Hadoop. All right, all right, great. So feel free to drop me a mail, and those who have signed up for the course, you should go to Ambari console, see what is running, what is not running, and see what all components are there in Hue. also browse the file system, which is HDFS, and realize that HDFS is just another file system, though beneath the hood it's running on data nodes and all. If you go to the hue, you can see that part. I'm showing you right away. Okay, let me just log in. You can see my screen, right? Or should I increase the font? So you can see the file browser. This is basically all the files over here. Create your own folder here under this directory structure. Create your own folder. These are other students folder. Don't fiddle with it. Right now I have not created separate login for everybody because I want everybody to see each other's work, right? So just create your own folder over here and start working on that. All right. And like for example, some of the data I have put in, these are the things that you can look at. So this is the file system, and it is stored right now on 4 data nodes. I'll be increasing the capacity as the load goes up. Okay. And this is the pig interface where you can write pig query, and this is the hbase sorry, this is hive catalog. And in case this is Oozie jobs, you can create jobs from here. And there are again hive interface and all, so you can write the query here. All right. So on the session, if you go to my courses, if you go to my courses here, under, you will only see one session, this one. Okay. And here I'll be uploading the recorded session. This is older one. This one will be uploaded here. You can take the quiz and have the presentation, look at the presentation. And installation instruction is very important. All of you should have a look at the installation instructions, right? This is very important because it has all the information about login, password, and everything. Okay. So devote some time to go through all of this. Do SSH to our servers. Okay, do SSH to our servers. And also, if you want, if you can set up your virtual machine. This instruction is again available in this installation instructions. I'm not opening that instructions right now because it has got authentication details. All right. Now feel free to, in case you want to go for because some of you are basically here for a demo session, you can, if you like the session, you can go for the full course. And in those full course we'll come taking care of making you understand the whole stack of Hadoop. And in general practices, when you have to scale up website, what you do, how do you build recommendation engine, and those kind of exercises will be going through the entire set, right? You'll have to devote working on exercises with us, otherwise the whole effort will be lost. All right. So this is pretty much from my side. Feel free to I mean, in case you liked it, you might put it in your blog or whatever. I will send you by morning this recorded session to you. All right. Good night then.